Welcome to Class Connect study series with Yusuf Arikewuyo. In our last class, we looked at the applications of equation of motion in solving motion-related questions. We were able to utilize the fact that all the equations of motion can be used in solving related questions by examining the parameters given. However, in today's lecture, we shall be looking at another way of solving motion-related questions that has to do with motions that do not move with uniform velocity or uniform speed. Today, we shall be examining the concept of instantaneous velocity, also called instantaneous speed. The instantaneous velocity of a body is the velocity of the body at a particular instant of time. That is, when we consider the instantaneous velocity of a body, we are looking at a particular case in a journey, what is the exact velocity with which the body was moving at that particular time. It differentiates itself from instantaneous speed in the sense that when we consider instantaneous speed, we do not consider direction. But in instantaneous velocity, we specify the instant with direction. It should also be added that when the body moves with a uniform velocity throughout the journey, then the average velocity and the instantaneous velocity may be similar. This is true if during the motion of the body does not change its velocity, that is, it maintains a uniform velocity. The moment the body changes its velocity, then the average velocity will not be the same as the instantaneous velocity. Let's consider this velocity time graph. We can see clearly that this body started from rest and it accelerated uniformly until it got a velocity of 18 meters per second in time t1 as indicated. Then it maintained this velocity all through T1, T2, T3, and at time T4 before it was brought to rest, let's say in time T5. In this particular example, we can see that the velocities at T1 is the same as T2, it is also the same at T3, and also the same at T4, so that the instantaneous velocity rather, at T1 is the same as that of T2, also that of T3, and that of T4. So that at any instance between T1 to T4, the velocities are the same. That is, the instantaneous velocity will be the same as the average velocity. Considering this particular diagram, we can see clearly that the velocities of this particular body in motion is not uniform. It only maintains a little bit of uniformity between T1 and T2, also at T3 and T4, and lastly between T4 and T5. However, the average velocities here will not be the same as the instantaneous velocity as we showed earlier, because the average velocity here would consider the changes in velocities between time t1, t2, t3 up to t5. That is, the velocities at between time t1 and t2 is not the same as the velocity between time t2 and t3, likewise not the same between time t3 and t4, and lastly not the same between time t4 and time t5, so that the instantaneous velocity in this case will not be the same as the average velocity. To obtain the instantaneous velocity of a body at any instance, we represent, let's say, the displacement x in terms of t. That is, x will now be written as a function of time, so that the displacement of the body would be written in an algebraic format. For example, we can say x will be equal to, let's say at random, 2t raised to power 3 plus 2t squared minus 4t. This here would represent the displacement of a body in meters or in other units as specified within the time interval of t in seconds. Then, to obtain the instantaneous velocity, all we simply do is to differentiate x, that is the displacement, with respect to t, so that we have v for instantaneous velocity will be equal to the x dt, a little bit of differential calculus. So that to obtain the differential of this particular expression, we have, if we recall from differential calculus, that if we have y equals x raised by n, dy dx is given as nx raised to the power of n minus 1. Then from our previous example of x equals 2t raised to the power 3 plus 2t raised to the power 2 minus 4t, we shall have the x dt to be given as 3 multiplied by 2, we have 6. If we reduce 3 by 1, we have t raised to the power 2 plus 2 multiplied by 2, we have 4. If we reduce 2 by 1, we have t raised to the power 1 minus the power of t in this particular minus 4t is raised to the power 1. 1 times 4, we shall have 4. T raised to the power 1 minus 1 will give us t raised to the power 0, and that gives us t raised to the power 0, which of course becomes 1. So we have the x dt to be given as 6t squared plus 4t minus 4. We should, however, be mindful of the following. 1. If the x dt is greater than 0, that means the body is moving away from rest in motion. That is, the body is in motion. If the x dt is lesser than 0, the body is coming to rest. And lastly, if the x dt is equal to 0, the body is at rest. Let's consider this question. The motion of a particle along a straight line is described by the equation x equals 2t raised to the power 4 minus 3t raised to the power 3. Find the velocity of the particle after 5 seconds. To solve this question, we shall apply differential calculus as we showed earlier. From the question, the motion of the particle was described as x equals 2t raised to the power 4 minus 3t raised to the power 3. So to obtain the instantaneous velocity after 5 seconds, we shall have the x dt will be equal to d dt of 2t raised to the power 4 minus 3t raised to the power 3. And this gives us 4 multiplied by 2, 8t raised to the power 3 minus 3 multiplied by 3, 9, reducing 3 by 1, we have t raised to the power 2. At t equals 5 seconds, we shall have v equals 8. Now substituting t equals 5. 5 raised to the power 3 minus 9, 5 raised to the power 2. So that we have 8 multiplied by 125 minus 9 times 25. This gives us 1000 minus 225. And of course, we shall get 775 meter per second. That means the velocity of the particle after 5 seconds is 775 meter per second. Additionally, let's consider this question. The displacement x in meters covered in time t seconds by a body is given as x equals t raised to the power 3 plus 2t raised to the power 3. Determine the velocity of the body at 2 seconds. To solve this particular question, we shall also apply differential calculus. We were given from the question that the displacement of the body x is given as t raised to the power 3 plus 2t raised to the power 3. And we were told to obtain the instantaneous velocity after 2 seconds. So what we need to do is to differentiate x with respect to t, and we shall have 3t raised to the power 2 3t raised to the power 2 plus 6t raised to the power 2. At t equals 2 seconds, we shall have that the velocity v equals 3 multiplied by 2 raised to the power 2 plus 6 multiplied by 2 raised to the power 2, which of course will be 3 times 4 plus 6 times 4, which is going to give us 12 plus 24, which is 36 meter per second. That means the velocity of the body at 2 seconds is 36 meter per second. Thanks so much for watching. Hope to see you in our next class. And please do not forget to subscribe and click on the notification button. Thank you.